Hello statistics students, my name is Emigh, and this video is our discussion on section 4.4. Title is Counting. All right, the first way we're going to learn to count, as if you didn't already know how to count, but there are different ways. It depends on what you're being asked to count. The first one is the fundamental counting rule, and the tree diagram here is a great display of it. This figure summarizes the possible outcomes for a true or false question, followed by a multiple choice question. So if you're taking a survey and the first question is true or false, that leaves you with two possible answers. But then based on your answer, if you select true, you then choose from A through E, or if you select false, you then choose from A through E. That gives us a total of true A, true B, true C, true D, true E, false A, false B, false C, false D, false E. That's 10 total possible answers. Well, if it's countable like that to 10, okay, great, we can do that. But if we're working with larger numbers, we can follow this formula. However many options there were for the first question, multiplied by however many there were for the second. And it can go on. If that then led to a third question, you would just multiply that by the number of possible answers through the third part of the question. And you can see here that ours was two parts, 2 times 5, which gave us 10 possible outcomes. So there are 10 possible answers. So if you were to ask to be asked, well, what is the probability of guessing correctly? What if I were just to walk in and just guess? I just went, okay, the answer is FB. So what is the probability that I guessed correctly? And the answer is 1 out of 10, or as a decimal, 0.01. So that 10 is really going to come into play as our denominator for probability questions a lot, because we know our denominators, probability fractions are the number of successes over the number of possibilities. So we're often using these counting rules, like this first one here, to count the number of possibilities, which is the denominator. All right, let's try another one. The number of ways different events can occur. Oh, this is the definition of the fundamental counting rule, not an example. The number of ways different events can occur, given the first event can occur m many ways, the next event can occur n many ways, the next event can occur o many ways, the next event can occur p many ways, the next event can occur q many ways, and so on. You just take those number of ways, let's say m times n times o times p times q, and so on, and whatever your result is the number of possible ways those events could occur. So m, n, o, p, and q. Well, let's use our example above with the true false. Our example just used m and n. M was 2, n was 5, and then we were done. So that's how we got our 10 possible ways the event could occur. Let me erase my scratch work there. All right, here's our example. In an advertising campaign, Applebee's offered a special 3-course dinner for $15.99. The menu included 3 choices of appetizers, 4 entrees, and 2 desserts. Oh, the question isn't really clear here. How many different 3-course dinners can you order? So how many, let me word it like this. How many different ways can you order this 3-course dinner? Okay, so there's our question. How many different ways can you order this 3-course dinner? Well, your first selection of appetizers has 3 options. Then you choose from 4 entrees. Then you choose from 2 desserts. So 3 times 4 times 2 is 24. So there are 24 different ways that you can order this 3-course dinner. All right, and that is called the fundamental counting rule. It is very useful, and next time you're at a restaurant, let's say like Chipotle or Subway, ordering, and you have so many different options for what type of bread or tortilla or a bowl first, and then what type of meat or vegetarian, think about the fundamental counting rule. And if you multiply up all those possible ways, you will know the extent of the variety of ways that you can order from restaurants like that. All right, the second counting rule we're going to cover is called the permutation rule. And this is the formula for it. Lowercase n is our number of objects, our total number of objects. Lowercase r is how many we'd actually be choosing. The numerator would be n factorial divided by the difference between n and r factorial. And you're welcome to do this by hand if you want. You have the algebra skills to do so. But I'm not going to show you how to do it using technology as well. And that's what most of you will default to, is the technology. And using a Texas Instrument or most graphing calculators, what you're going to do is enter your total number of items. Then you're going to hit math. Math on my TAI 84 is in the very first column, the fourth key down. It says math. Then you're going to select probability. Then this is the name of the program. Okay, it's n permutations. Choose R, many objects. You'll have to tell it R, and then you run the program. Okay. What that will output for you is the number of different permutations when n different items are available and R many of those items are selected without replacement. Rearrangements of the same items are counted as different permutations. And this last line right here is the, I would say, one of the more confusing parts when you are trying to differentiate between permutations and combinations. So if you are asked to count the number of permutations, then anytime your items are rearranged in a different order, you count that. You say, okay, that's a different permutation. Versus if you're asked to count how many combinations there are, if you rearrange the items, you don't count it as a different combination. So even though both those things exist, you have to really focus on, are they asking me to count the permutations or are they asking me to count the combinations? We'll see some examples that will help explain more. Erase all that. All right, here's one example. To win an exacta bet in racing, you must choose the horse that finishes first and the one that finishes second in the correct order. Okay, we're gonna focus on that, in the correct order. If there are 20 horses, okay, that's our lowercase n equals 20, what is the probability of winning with one ticket? Okay, lowercase n equals 20, and we are going to choose 2 horses. Oh gosh. Going to choose the horse that finishes second and the horse that finishes first. So we have r equals 2. Okay, now I want to get into the discussion of, are we supposed to be counting the number of permutations or the number of combinations? And the question doesn't specify, so you have to be able to decide. And so let me try to give you a visual. First place, second place. If that is my ticket that I'm purchasing to bet, and this is your ticket, okay, and let's say I choose Star is going to win first, and then Lucky is going to take second. And let's say you choose the same 2 horses, but you say Lucky is going to take first place and Star is going to take second. So my question to you is, are those 2 tickets different? Okay, if you said yes, you are correct for this type of bet. This particular type of bet says that you must choose the horses in the correct order. Some people say order matters, and if order matters, you're talking permutations. Contrary to a type of bet where you just had to choose the top 2, horses that finish, these would be the same ticket, and so it would be counted as one combination, okay? But it's 2 permutations. It's not always easy for that to set in at first, but give it some time. All right, so we're going to take out our Texas Instrument. Let's do this together. Turn it on. Okay. Each version is a little different. These directions right here are in from the TI-83. So type 20, because that's your total number to choose from. Then hit Math. Now you're going to arrow over it's 3 times on mine to where it says probability. Okay, if you look at your list of probability programs there, you have RAND, NPR, NCR, there's that factorial key. We want to choose NPR. So go to that program and open it up. And then input the 2, that's your R, how many you're going to select out of the 20. And then run that program. And if you did it correctly, you should get 380. Oops. So the output will be 380. But the question was not how many different permutations are there. The question was, what is the probability of winning with 1 ticket? Well, if there are 380 possibilities, that means you have a 1 in 380 chance of winning with 1 ticket. Let's do another one. A history pop quiz asks students to arrange the following presidents in chronological order. There's that word again, order. I've heard a lot of people learn and teach it as order matters. If the different order matters, you're talking permutations. So, well, you have to decide if order matters. If you're the teacher and someone turns in their quiz and they've put these presidents down in that order, let's say, and a different student turns in their quiz and they put the presidents down maybe in reverse order, are those 2 different quizzes? And the answer is yes, because this quiz was testing chronological order. If it just said name 6 presidents, okay, fine. It doesn't matter which order you write them down. That would be combinations. But it says to write them down in chronological order. So we are talking permutations. All right. Let me erase my patchwork there. Okay, we have 6 items to choose from. 6 presidents there. And in this quiz, we have to choose all 6. So that's why you see 6, choose 6. So n equals 6 in this question, and r also equals 6 in this question. Above, n equaled 20, and r equaled 2. And that's okay. If you have to choose 2 of the items, that's fine. And if you have to choose all of the items, that's fine too. This permutation rule works. Okay, so go ahead and pick up your calculator again. Hit 6, math, arrow over to probability, arrow down to our program, NPR, hit 6 again and run that program. And if you did that correctly, you should get 720. But remember, that's just your denominator because the question is, what is the probability of guessing correctly? Well, there's only one correct answer out of those 720, okay? Now, had it just said how many different ways are there to answer, then you could go with the 720. But if it says what's the probability of guessing the correct way, then it's 1 out of 720. So heads up for that. Okay, the third rule is the combinations rule, and we've already started discussing it, so that's nice. You can calculate it by hand using that formula if you would like. You have the algebra skills to do so. The output will be the number of different combinations when n different items are available and many of them are selected without replacement. So very similar to permutations. It's actually been found in the same place. You'll do n, total number of objects, math, go over to probability, scroll down to NCR, enter R, that'll be the number of items you're actually going to choose, which could be all of them, as you guys just saw, and then you'll run that program. And it'll most often give you the denominator necessary for a probability question. Okay, here we go. In the Match 6 Lotto, winning the jackpot requires you select 6 different numbers from 1 to 9. The winning numbers may be drawn in any order. They're trying to help us out here. It does not matter the order, any order. So just how many combinations are there of these numbers from 1 to 49? And then we're asked, what is the probability of winning with 1 ticket? Okay, N is 49. So type that on your calculator first. And then hit math, arrow over to probability, choose the program NCR. We are selecting 6 of the items this time, so R equals 6. Run that program. And if you ran it correctly, you got 13,983,816. Making the probability of winning 1 over 13,983,816. So if you only buy 1 ticket, the chances of you getting the winning ticket are very low. I want to see that as a decimal. 1 divided by 13,983,816. I got 7.5 times 10 to the negative 8. So that's scientific notation. That'd be 0.6 zeros and a 7 probability of selecting the winning combination. So interesting to know. All right. Some mnemonics of permutation and combinations that have helped students and any learner are permutations, positions. They both start with the letter P. Rearrangements of the same numbers result in a different outcome and is counted as another permutation. For example, if you're talking presidents, vice presidents, secretary, treasurer, let's represent them with W, X, Y, and Z. That would be a very different outcome than if Z person was the president, Y person was the vice president, Z person was the secretary, and X person was the treasurer. This is a very big difference, and in that case, you would count these as one permutation and then a second permutation, and every time you rearrange them, you would keep counting them as different permutations. And for this particular case, there would be 24 permutations in all for those positions. If you're curious where that came from, it goes like this. Fundamental counting rule. I'm going to show you here. You have 4 positions to fill. Sorry, it's my dog barking, the mailman. Okay. 4 people and 4 positions to fill. When you choose your first person, let's say whoever's going to be the president, you have 4 options. So 4 to choose from. Well, then when you go to fill the vice presidency seat, let's say you're going in that order, you're down to 3 people to choose from. When you go to fill the secretary position, you're down to 2 people. And when you get down to the last person who will be your treasurer, you have 1 person to choose from. And that's 4 times 3 times 2 times 1. Shorthand in mathematics, we say that's 4 factorial, and that equals 24. All right, I'm going to erase that now. I just wanted you to know where that 24 came from. Combinations and committees both start with the letter C. Rearrangements of the same members resulting in the same committee is not counted as another combination. So if you're talking committee members, W, X, Y, and Z, and then you rearrange them, you still have the same committee, Z, Y. Oops, I did a typo there. Z, Y, W, X. It's the same committee of 4 people. The positions on the committee don't matter at this point, at least, as far as we know. So that would just count as 1 combination of these 4 committee members. So I like this this slide showing that there can be 24 permutations of 4 people, but only 1 combination of those 4 people. That's quite a difference. So you just have to make sure you're counting whatever you're being requested to count, permutations, or you're being requested to count combinations. All right, I'd like you to pause this video now and try these 4 examples. Welcome back. Grade your own. Let's see how you did. If you put 84 for question number 1, you got it right. Nice job. You would want to use 9 as your N, math, then probability. In CR, we're talking combinations here, and then 3 as your R. Number 2, if you got it right, you put 504. One way to get that is 9. Oh no. Yeah, math, probability, in PR, and then R equals 3 this time, and run that. So the first one, it was a committee where the positions didn't matter, so we use combinations. Oops. It was a committee where positions didn't matter, so we use combinations. And in the next one, we have positions, chairperson, secretary, treasurer, so that's why we use permutations. Number 3, if you put 7,893,600, and the probability of that, guessing correctly in one try, is 1 over 7,893,600. You got it right. Nice job. One way to come up with that is using the fundamental counting rule. When you're choosing your first digit for your password, you have 26 options. But it says repetition is not allowed. So when you're choosing your second digit for your password, you have 25 options. And when you choose your third digit, you have 24 options. When you select the fourth digit for your password, has to be one of the lowercase alphabet letters. Repetition's not allowed. You're down to 23 letters to choose from, and then 22. Last one, if you put 12, you got it right. Fundamental counting rule again. 3 options to choose from, then 2, then 2 more. And that will conclude our discussion on section 4.4. My name is Jamie Emigh. Thank you for joining me. I'll see you next time for our discussion on 5.1.